Hello, Patreons, and welcome back. This is part 2 of our DC circuit series, in which I'm teaching on DC circuits. But anyways, we're going to use some common items like we used before, such as the breadboard. And if you haven't watched the first video in this series, we went over basic elements of a circuit, discussed what a circuit is, as well as covered resistance parameters, series versus parallel resistors in the previous video, discussed current dividing rule, voltage dividing rule, and made ourselves a resistive network, and then demonstrated that resistive network on our breadboard with some LEDs. Moving on, we're going to get into inductors. So if you have a box of inductors handy, assorted inductors, I suggest getting that out, as well as capacitors and their purpose in the DC circuit. So without further ado, let's get started. Now, what I've currently done is basically build a circuit just like this. I'll hold this slightly closer to the camera and give you a second to focus in on it. But essentially, we have our DC power supply that I have sitting over here to the left. That's going to supply a 5-volt reference DC voltage into two 1 millihenry 6 by 8 millimeter inductors. Okay. And then, of course, out the lead of the second conductor is our return or ground going back to the supply. Now, if I power this up, I don't want to power it up for too long. Let's use a little cheat here. Use electrodoc. And we'll go to Ohm's law and have 5 at 10 ohms total. Well, how would you know that they're 10 ohms? Right now that power supply is not powered up. But we can go across the leads and check real quick. We got 5 ohms here, 5 ohms here. So we should have about, from the supply, we're going to have half an amp pool, so 500 milliamps. Voltage equals V equals 5, resistance equals 10, I equals 500 milliamps. There we go. Cheat right here, and then our power dissipation 2.5 watts. So we're not going to keep it powered up for too long because it's a bit too high amperage for the circuit this simple circuit in my opinion. But we can do some testing of it at the minimum and learn a few things. Now, first off, what is the purpose of a inductor? Well, or actually, what is an inductor? Let's discuss that first. Well, essentially, what you have is a conductor, such as a copper wire, typically enameled, that's going to be wrapped around a ferrite slug or core. Okay. Something like that is a demonstration, although this is a Q-tip and not a ferrite slug or ferrite core. And with our inductors in circuit, we have something called inductance parameter. Now, according to Faraday's law of electromagnetic induction, a change in current, say sinusoidal waveform versus direct current, which you would have with a DC supply. But anyways, a change in current produces EMF, or an electromagnetic force, of self-induction in a coil of wire, which varies directly with the rate of change of current with respect to time. Now, mathematically, what this means is we have the equation E equals L di, delta T. So inductance L is our current over time, or delta current over delta time. All right. That's the basics. And then L is or our inductance is a proportionality factor called as the coefficients of self-inductance. Inductance can be defined as the property of a circuit element by which energy is capable of being stored in a magnetic field of flux. Well, interestingly enough, I mean, traditionally in circuits, you may see, and I'm actually going to remove my ring since we're going to be working on live circuits. Remember safety. But if you have ever seen something like a relay in circuit, you know, it's basically a coil or an inductor with essentially a latch, and as current goes through the coil portion, basically the inductor, electromagnetic fields are created. Okay, and it's these fields that pull our latch closed, which, you know, basically is what's energizing the relay, and then whatever's over on side of the latch in circuit, say if it was resistors, capacitors, whatever, that whole circuit over here is now closed. Hopefully that makes sense. And then, of course, in the application of our circuit itself, you know, as I stated, an inductor's purpose is to pass DC and block AC. If I didn't mention that, that's basically an inductor in and of itself. You know, it's going to allow the direct current to flow through whatever is in circuit, but AC is essentially going to be blocked. So you can say you have a part of your circuit that's going to have AC writing a DC reference on it. Say both of these reference voltages are in one circuit. Well, you could use an inductor, and this is just you know, a hypothetical. Say we have AC and DC. Now I realize that's pretty terrible drawing. AC and DC here within our circuit. Well, through the inductor, we should only see the DC component over on this side. So you could use it to basically decouple a circuit, or you can also use it to filter DC out of your circuit. So let's pretend that this inductor is no longer there, and now it's between here and, let's say this is our negative ground, positive negative. Well, our DC component should be allowed to ground through this way, but our AC component essentially is allowed to pass through this portion of our circuit. So that's essentially what an inductor does. Now, one of the distinguishing factors of inductance is that it makes itself felt in a circuit when there is a change in current. So typically you'll find inductors in things like a DC power supply where you're converting AC over to DC. A lot of times they'll be in those wall warts per se. I think in the video where I repaired that Four Moms Rockaroo, I destroyed the DC power supply, and on the backside of it I broke one leg off of the inductor that was there to get rid of ripple off of your DC. Again, filtering in that capacity, but any AC ripple should have been filtered off by the inductor. Now, if we are applying direct current to a circuit containing inductors only, then in that case the inductor will simply behave as a short circuit per se. In ideal case, an inductor is considered a resistance-free component, but as measured here now, we know that to not in an ideal world resistance-free component, but in application a lot of times that's simply not true. And that is because although although in practical it must contain the resistance of the wire out of which the inductor will be formed, i.e. that enameled copper wire that's spun around the ferrite core that's in the center of what makes or builds this component. Well, what can we say about an inductor in this circuit right here and learn a little bit from? Remember we briefly talked about Kirchhoff's voltage law in video 1, where our voltage equals voltage 1 plus voltage 2 if there were several components in a circuit, so the sum of our voltage dividers. Well, we could also say that V1 equals, let's look up here, we're going to combine these two, we'll call this L1 and L2, but V1 equals L1 over delta I, or times delta I over delta T. Conversely, V2 equals L2 delta I over delta T. Oh, V1 equals L1 times our I'm drawing a blank on common terminology, so forgive me, times our current over time, change in current over change in time. And again, V2 equals L2, or our inductance, times the change in current over change in time. So hopefully that makes sense to you. And then with these two formulas right here, we can essentially write them out as either V equals L1 plus L2, oops, let's put that in parentheses. I'll rewrite this. V equals L1 plus L2, put it in parentheses, times delta current over delta time. Or you can write this out as V equals Ls times delta current over delta time. And essentially, Ls is the sum of L1 plus L2. No, I kind of got off a little bit there, but I'll give you a second to look at this and write it down if you need to. Now, given this formula, we could say that the sum of our inductance is our 1 millihenry inductor here plus our 1 millihenry inductor here. So essentially we have 2 millihenries of inductance in our circuit, if that makes sense. Now, because that it does kind of act like a voltage divider, although as I previously stated, in circuit, in an ideal world, an inductor would have zero resistance, we would still get a voltage drop. As a matter of fact, if we were to do the voltage divider rule with a 5-volt source and two 5-ohm resistors, which they are not, they're inductors, we should see a voltage between this, a drop of 2.5 volts in circuit. So I'm going to turn on my power supply for a minute. I've got it set to 5 volts, and we're right about 400 milliamps in circuit. And I'm going to set my multimeter right here, and let me get this light out of the way for you for a second. Ooh, maybe that's not so good. It's causing my camera to go off, but we'll just take this from positive lead to negative lead here, and you should be able to see that 5 volts. Now it's under a load, so if I was to disconnect it, you'd see it jump closer to 5 volts. But if I go between here and then check in the middle of my circuit, i.e. right here, we can confirm that voltage has been dropped across the first inductor. So let's go here. And there you have it. 2.4, almost 2.5 as mentioned. Which basically sets up our series combination of inductor and how it works in circuit. So what is that? What can we say if they were placed in parallel? Well, give me a second. Well, moving into our parallel circuit, which I have drawn out here and placed our inductors in parallel over here, what I'm going to do is I'm going to drop our supply voltage down to 1 volt instead. So that way not as much current will be drawn through the circuit. So we can say that our voltage is equal to V equals 1 volt. Now, our current, as we well know, this total current of our circuit is the sum of our current that we find here of this inductor, first inductor in parallel, and the sum of the current coming across, going through our second inductor that's in parallel as well. So by adding up what the current would be through each inductor, we would have our total current for the circuit. As both the inductors are in parallel, hence the potential difference across both the inductors will be the same. Now, again, this is going back to Kirchhoff's law, or his current law versus voltage law, in consideration of our circuit that we have here. Now, assuming 0 initial current through each inductor, from our previous from some of our previous equations, we can still do a bit of math. For instance, initial current in the inductor is 0. If it is 0, then we can, what are we looking at here? We're looking at I equals 1 over L. Then our integral is going to have some limits, so time and 0 times the delta voltage times voltage, and then our delta over time. We could say that I1 here is I1, or our first measurement in which we're trying to determine current, equals 1 over inductor 1 our integral and voltage times the times delta, the difference in time. And then we would say the same, I2 equals 1 over L2 V dt, just like that. Okay? And then from these equations, we can develop other things. Let's move these equations, kind of make them look better. If we were looking for the sum of our current, so I1, I2 from this information here, if we didn't know what they were to solve for this, we could essentially say that I equals this times, or this plus this, okay? So our sum here would be this plus this, or we could express it as I equals, let's see, 1 over L1 plus 1 over L2 VDT. So here goes one way to express it instead of just I this plus this. And then another way we could express that is I equals 1 for LP, which would be combining these and our integral VDT. So here basically is our second way of expressing that. And then essentially what this comes out to is 1 over LP equals 1 over L1 plus 1 over L2, which is basically the equivalent inductance of two parallel connected inductors. And it can also be written as, we'll take the inverse, we're looking at LP equals L1 times L2 over L1 plus L2. Which, if you remember this from our previous video, this is very similar, if not the same, to the equivalent resistance of two parallel connected resistors. Now we're just doing it for our inductors. So if we were to write this out, remember they were 5 ohms each, basically, or what? 1 microhenry, 5 ohms, essentially. Well, they were 1 millihenry, so 1 times 1 equals 1 plus 1, so 2. So essentially, 1 times 1 over 1 plus 1 would give us 0.5 millihenries. Now, if you recall, they did also have about 5 ohms of resistance because of the copper wire. So if we were to do the same there, 5 times 5 is 25 over 5 plus 5 is 10. If we were to calculate for the resistance in circuit, we should get essentially 2.5 ohms. Now, I don't have any way of measuring the millihenries, but I can with my multimeter at least prove to you. My supply is currently not connected. The combined resistance of these components in parallel. And what do we have? Yeah, there we go. 2.5, 2.6. I'm slightly bouncing around. And we could essentially say that if our voltage is 1 volt and our resistance is 2.5 ohms, then now I'll just go back to my cheater. Dual math versus cheating. Always choose cheating. But at 1 volt, we shouldn't see any more than 400 milliamps in circuit. And if we were to divide them up across each circuit, where you would only see about 200 milliamp per each branch. So at I1 and I2 would both be 200 milliamps. But the big question is, if we use the essentially the same rule here, Ohm's law to calculate current inside of this circuit, is it going to be correct? Well, it gave me 400 milliamps total for the circuit. What does my power supply show? Oh, it's a bit off here on camera, but let me hook it up. And what I've done is I've gone ahead and took my multimeter and lifted one leg to one of our inductors and put it in here. So that way we're just measuring current down one side, but we're only seeing about 80 milliamps going across basically L2. So is there something else at play here because they're inductors and not resistors? And the answer is essentially yes. I mean, let's go back to our formula here. Well, if I were to insert L1, which is 10 millihenries, excuse me, and L2 is 10 millihenries, 1 divided by 0.1 divided by 10, so we're looking at 0.1, 0.2. So we're essentially coming out to 200 milliamps from our power supply, which it's reading a little bit low. It's reading just under 200 at 196. And then if you essentially divide that in half, you can see that we're getting 86 amps down, milliamps down one side, and there'd be 86 down the other. And normalizing this and putting my multimeter directly in line with the incoming source voltage supply, we're actually measuring if I can get it to my finger to stop slipping. There we go. 200 milliamps as we just calculated. With inductance parameters out of the way, we'll now move into capacitance parameters. Now what I've gone ahead and done is I've taken two 100 microfarad 16 volt caps and put them in circuit over on my breadboard. The DC supply we'll put through them is 5 volts, so we can already know what our supply voltage is. Now capacitors, the capacitance parameter is our third basic parameter of electrical circuits. A capacitor is an energy storing element, okay, in which energy is stored in the form of an electrical charge. The charge stored between two plates of the capacitor, these are electrolytic capacitors, these here, is directly proportional to the potential difference across the two plates. So essentially, we're looking at Q equals CV, wherein Q is the charge stored between the two plates. C is the proportionality factor known as capacitance, and V is the potential difference across the two plates. And as in general, the current is expressed as I equals delta charge, or delta Q, over delta time equals capacitance delta voltage over delta time. And then the delta time equals 1 over capacitance times inductance delta time. And then voltage equals 1 over capacitance. And then we use that integral, inductance delta time plus voltage 0. Where there is no initial voltage across the capacitor in this case, so essentially, ignoring the 5 that I mentioned up here, V equals 1 over capacitance time 0, inductance delta time, so no supply voltage. The graphical representation of this would look something like, let's see, if we were to plot this out, where I dt is our amperage, and this will be volt scale going this way, so amperage and volts. Here is 0. Our slope is essentially 1 over capacitance. So probably more like this, but just to draw a little bit of a diagram. Now, what I would like for us to do, though, is consider our series combination of two capacitors, C1 and C2, which we have here, both 100 microfarad caps rated for 16 volts. Now, when a voltage is applied across the combination, the capacitor will have equal displacement of charge, but the potential difference across the terminal will be different, provided C1 is not equal to C2. So actually, what we should do is remove, since they are equal, I'll take out this 100 microfarad cap here, and I'm going to replace it with a 22 microfarad cap rated for 16 volts. Now, the function of a capacitor is basically the inverse of a resistor. Not resistor, excuse me, an inductor. Where an inductor is designed to filter out an AC component and only pass a DC component. A capacitor is designed to filter out a DC component but allow an AC component through it. Let us move now into Kirchhoff's voltage law, which is basically, again, our total voltage equals V1 plus V2. So V1 plus V2. All right? And for zero initial capacitance voltage from the equation would be essentially, let me move my multimeter out of the way. I know my paper is getting a bit jumbled up here, but bear with me. V1 equals 1 over capacitance 1. And remember what we essentially wrote out here. Our integral current over the change multiplied by the change in time. And then V2 would essentially equal the same thing, 1 over C2 I dt. There we go. Or if we were to insert essentially these equations for voltage, we would show that as voltage, our total voltage, is essentially 1 over C1 I dt, and I know my handwriting gets a bit sloppy, plus 1 over C2 I dt. Okay? Although this is probably not easy to read through. So how can we simplify this? Well, we can essentially rewrite this as, let's see, V equals 1 C1 plus 1 C2 in parentheses. Pull out our integral I dt. So essentially we could rewrite it as that, or V equals the sum 1 over our capacitance sum, and then looking at our integral I dt, wherein essentially 1C, the inverse of our total capacitance, 1C equals 1 over C1 plus 1 over C2. And this is basically our equivalent capacitance of two series connected capacitors, which can also be written as the sum equals C1, C2 over C1 plus C2. Given we have two different capacitance values, I went ahead and wrote it out. Essentially, 100 microfarad times 22 microfarad, which is 2,200 microfarad, over 100 plus 22, so 122, which essentially gives us, I put in my calculator, let's see, 2200 divided by 122, total capacitance of 18.03 microfarads, which, man, isn't that quite a bit different than the sum of a resistor in series? This is almost like the polar opposite. And if you were to say that, essentially you're right. It's akin to measuring resistors in parallel versus resistors in series. Oh, I went across the wrong leg, I believe. There we go. 18.8 is what I'm measuring. So it is essentially clear from the equation that we have here that when two or more capacitors are connected in series, then they can be treated as resistance connected in parallel. Hence, the equivalent capacitance in series circuits can be calculated in the same manner as equivalence resistance is calculated in case of parallel circuits. Well, if that's how capacitors function in series, the inverse of, or the opposite of resistors in series, more like resistors in parallel, then how do capacitors behave in parallel in circuit? Now, remember me saying that a capacitor is designed to allow AC to pass through it, but not DC. I've essentially removed that 22 microfarad capacitor out of circuit before we get into the parallel discussion, because I wanted to show you something. I've got my supply hooked up, and we can see the 5 volts on one side of the capacitor there, but on the other side there's nothing. As a matter of fact, my DC power supply is not showing any current drawing through the circuit. Now, if I was to remove this lead out, and let's put our 22 microfarad capacitor back in series with our 100 microfarad capacitor, and we put our circuit back together. Now I want to show you something. We still have, I've got my leads backwards, but we still got 5 volts going to the first capacitor, but look, coming out that second leg. Because we've charged it a bit, we're showing that we have almost a full drop in voltage there. Almost 5 volts drop, but 0.7 basically volts coming out to the second capacitor, and then at the output of that is 0. Well, let me discharge this cap real quick. Fun. Hopefully that's discharged. And we will put it back in the circuit. All right, back in. 5 volts. We're seeing a 4 volt drop across that capacitor, or a 1 volt drop. So we got 4 volts going to the second one, but we're still 0 out of the end of it. So I wouldn't say that you could use a capacitor to voltage divide anything, because you can't. Essentially, they're only storing up to what balancing basically the potential that's stored between the two is what's occurring. So if this capacitor was to store the greater portion of electrical current coming through, then this would have less to store, as we saw when we just had this removed and only this guy in circuit charging it up. Letting it sit at that charge, and then throwing this other capacitor in. And let's see if it went back to that entire 4 volt drop. Yeah, almost the entire 5 volts is dropped off that first capacitor because it's charged up. But I just wanted to annotate that real quick before we get into how capacitors behave in parallel. Okay, this is our last bit of equations, and I promise you I'll stop after this. So I just went ahead and wrote out everything so I could talk through it instead of talking while writing, because I'm not very great at doing that. Here goes our second circuit, where essentially we have capacitor 1, which is a 100 microfarad cap, and then capacitor 2, which is a 220 microfarad cap in parallel in our circuit. And now, considering two capacitors that are connected in parallel, as both the capacitors are connected in parallel, the potential difference across both of the capacitors will be the same. Okay, so our difference will be the same. Okay. Now we apply Kirchhoff's current law in this case, and then from the equation we would say that our total current would be the current of I plus the current of I1 plus the current of I2 going across capacitor 2 and I1 across capacitor 1. But from the equation concerning Kirchhoff's law, we would state it as I1 equals C1 times the difference in voltage over the difference in time, okay? Delta V over delta T. And then I2 equals capacitor 2, its capacitance, multiplied by the difference in voltage over the difference in time, okay? Or delta V, delta T. And from the equation, we would say that our total current is capacitance 1 times dV over dt plus capacitor 2 times dV over dt. Hopefully this makes sense. And then in order to write these equations out or express them in a different way, we could pull out this from here and there, and we could say C1 plus C2 in parentheses times dV over dt. And then we could also talk about it in this case and say that our current is equal to the total capacitance times dV over dt, wherein Cp being the total capacitance is C1 plus C2. Now what I've done is I've set my multimeter to measure amperage, and I've put it between my 5-volt supply and then the pin going in. But again, because remember these are capacitors and they're storing that DC charge right now, there's no current moving through the circuit because it's just not allowing it to pass through. It's storing the charge until it needs to be discharged, okay? Now can probably demonstrate that for you, and hopefully a somewhat safe fashion by shorting across one of our capacitors. Hopefully not too sparky. There we go. Shorten through it. And you can see that current, if you didn't see, I'll move my hand a bit and do it the other way. You can see that current jumping up as I short across it until I remove my shortening device and allow the capacitors to do their job. Okay, but that current is shared between each capacitor as previously mentioned. Oh, and one more thing. Let me. I've removed my DC power supply. It's no longer connected up. Probably just do like this right here. Remove these gator clips, that way it's easier for you to tell that. But there we go, they're out of the way. No longer connected up, but shorting out these capacitors because I want to measure them, and you do not want to measure a capacitor with a DC voltage stored on it. But anyways, those should be shorted out fairly well. Remember, Cp equals C1 plus C2, and when they're in parallel. So I got this on capacitance. Yes, I do. And when we measure it, 100 plus 22, we should be seeing 122 microfarad, barring if they're how close they are to their actual tolerance. My finger touching it's going to be a bit of difference, but we're looking at 110, so we're a bit out of talk. Slightly, I don't know about. I'd have to do the math in my head, but essentially 1% out of tolerance there, and 109, or excuse me, 9% was 10%, and 23 over here. So So 109 and 23, and we get, I think it's making contact in that circuit. There we go. Now they're summed, 131, 32, whatever. But you know, it can be concluded essentially that capacitance in parallel can be treated in the same manner as resistance in series. So essentially, because we don't have a difference in voltage over difference in time, we're not in the AC circuit, we'll negate this out. But as part of a component, you're essentially saying that you know, 100 plus 22 is 122 microfarads in circuit, which would be true. And then our current, because this is 0, well, 122 times 0 is, of course, 0, because there is 0 difference in voltage, 0 difference in time. So there you go, which now makes me want to consider, well, how can we demonstrate the function of a capacitor and an inductor in a DC circuit when there are also, you know, and not much going on unless if we apply an AC voltage versus a DC. I'll come up with something and come back. Now, on to our circuit in this demonstration. Well, essentially, I've taken my signal generator or arbitrary waveform generator to produce a 10 kHz signal at 10 volts peak to peak, and I set it up to represent a full wave, essentially because it's going to act as a full wave bridge rectifier. And then this circuit we have down here is going to be essentially what we're going to use to get ripple off of our rectified voltage, okay? And then I put dash lines here. I meant to make these dash lines, but we're going to be pulling a 10 microfarad capacitor in and out circuit here. And then our 20 microfarad capacitor is going to remain over here. Then we have two 220 ohm resistors up top, and then our 1 micro Henry inductor sitting right here. Okay, so that's basically our circuit. Now, concerning our, if I can reach up there, there we go. Concerning our signal generator, well, let's take a look at it on our oscope right now, right here. So you can physically see the signal that's present. Okay, keep that signal in mind, all right? Now, if you're following along doing this circuit along with me, I suppose I should probably state you're doing so at your own risk. That being said, the current's limited enough in this circuit, I feel relatively safe. And I would also encourage, you know, swap out capacitors, swap out resistors, swap out inductors, and see how that's going to change the output of your signal. Now, I also want to bring in my voltmeter here, my digital multimeter, and just make a few preliminary measurements. It looks like we're essentially developing 2.8 volts DC. And what is the ripple or AC component of that signal? 500 millivolts AC. So I'm going to write those two things down. And I actually previously recorded them, but they are right here. I don't know why I'm drawing through this. We'll just put it in the middle of this box. 2.8 volts DC with a bit of ripple, which is 0.5 volts AC, or 500 millivolts AC. Okay, so that's going to be our initial comparative values. And so now I just kind of want to hook this all up in circuit. Let me put my oscope probe down here, negative probe to there. And as far as my supply goes, Try not to get it so much wrapped around that lead. We'll put our negative lead here. Then I'm going to come across this way and put in my positive lead. This side. Okay. Now we have a live circuit. And I want to look at my first resistor here. And we've got that full wave sitting right there. What about right here? Well, it looks like we've reduced the amplitude of it there. What about leading up to this inductor? Oh, would you look at that? We virtually eliminated the whole thing in circuit. So we got a nice pretty DC signal there. Well, let's take our multimeter here and let's also look at a couple things. First, we'll test out the AC component of this signal. We still got essentially that 500 millivolts there. We reduce it to 0.2 millivolts here. And then it's eliminated here. So I kind of want to write that down. So on the AC side, first example, 0.5, 0.25, and then 0. Okay, 0.5, 0.25, and 0. Now let's check out our DC component of this signal. We have 2.8, 2.8, 2.8. Interesting. Okay. Now, with my oscilloscope hooked up, I kind of want to put this 100 microfarad cap between the first resistor and ground to see what occurs. Did anything happen up on the screen? Doesn't appear so. But let me go back to this first component and take a look here. Well, it looks like at our first resistor, we've kind of filtered out a bit of that AC signal before going into the resistor. Done so again here, here. Interesting. Okay, let's look again at our AC and DC components. Well, before we got 0.5 volts ripple right here at the beginning of my resistor. Now we're getting essentially nothing throughout the entire circuit. Okay, what about the DC component? 2.8, 2.8, 2.8. Interesting. Well, let's remove this 100 microfarad cap there. Now we got that ripple back through here. And let's put it at the very back end of here. Put it in parallel with our 220 microfarad, or excuse me, our 22 microfarad capacitor. Actually, what I want to do is reduce my amplitude below 1 volt. I'll kind of move that to the bottom, because even though we're not measuring it, you can kind of see a little bit of ripple on that DC. Not much, but you still see a very little amount. So let me move that further down. Yeah, super little amount. And I'm just going to put this back in the beginning again. So we know a capacitor here definitely eliminates ripple in the entire circuit. And then our inductor and basically our LC circuit here is essentially removing the remainder of that ripple. But you can see when I put in the capacitor at the beginning, it removes some of that. It might be hard, some of that. So this is capacitor in, capacitor out. You see how that DC signal gets a little bit dirtier when I remove it out? Now let me put it back, let me put it over here on the end stage in parallel with this last capacitor. Do I have it in there? That's hard for me to tell. Let me get my lead situated again. Okay, now we got it in there. You can see it cleaned up that signal. But did it change anything up front? Oh no, definitely did not. Definitely didn't change anything at the front end, but it definitely cleaned up our output. So let's look again at our AC and DC components. So on the first try, with the 100 microfarad capacitor at the beginning stage here, we, with no capacitor, we had, no capacitor at our beginning stage here. We had 0.5 volts of ripple. After the voltage divider, 0.25 volts of ripple, and then none at the output. When we threw the 100 microfarad capacitor in at our beginning stage here, we essentially eliminated that ripple across all 3 points. Beginning, voltage divider, output stage. So all here were 0. Okay. Now, with our capacitor at the back, we do have a much cleaner signal, just like we did with it at the beginning. But I want to look at our stages again to see if there's any difference. Well, we saw a difference on the oscope, so let's measure that difference with our multimeter. At the beginning stage, we have 0.45, we'll call it 0.5. At the voltage divider stage, 0.25. And at our output, 0. So that's interesting. 0.5, 0.25, and then 0. So barring where our 100 microfarad capacitor is in circuit, if it's not in circuit, we have 0.5 here of ripple, 0.25 there of ripple, and 0 ripple at our output. If we throw that 100 microfarad capacitor at the beginning of our circuit, then we essentially have 0 ripple all the way across. And mind you, none of this had an effect on our DC component. And then if I then if I move that 100 microfarad in parallel with our 22 microfarad, we're back to 0.5 here, 0.25 here, and 0 there. The big difference is we either eliminate ripple across our entire series of resistors here, or and pretty up our signal, or we don't eliminate it, the ripple seen across these resistors here. We just put the capacitor at the end. We have a cleaner output, but we still have ripple at these components here. Well, what might be the case in which we don't need ripple here, but we still need a pretty signal? Well, I would say, well, let me first ask this question. As it stands right now, we've essentially filtered out the ripple on our full wave signal coming from our signal generator. So we have a nice, pretty, clean, 2.8? Yeah, 2.8 volt DC signal coming out. Okay. So we have a very clean 2.8 DC signal coming out as it stands right now, but we do have ripple across these resistors. Well, what if I need a very clean DC signal here, but also need a clean DC signal here? For instance, what if I had LEDs in this circuit? Let me grab an LED. Now, in order to do this experiment with an LED, what I've done is essentially removed one leg of this resistor out of circuit with the other leg, and as you can see, we've got that half-wave bridge rectification sitting in there. And what I'm going to do is I've taken this, this is a color flashing LED with a forward bias voltage of 3 to 3.4 volts, and I'm just going to stick it after this resistor here, okay, and put it between there and ground. Now notice all the lights are essentially on this thing right now. Not flashing, not color changing at all. Okay? So in our schematic, it's essentially between this point here and this point here. Well, that's one part of the circuit. Now we need to essentially finish it out, because all these other components from this point onward have been removed out of circuit. From this point onward has been removed out of circuit, and so all we have is this 220 ohm resistor with 2.8 volts going through it, and then essentially the LED to go into ground right here. Well, let's throw this resistor back in circuit and let's see what happens. Would you look at that? It starts to color change on us. Isn't that cool? However, right at the get-go there, and I've got my oscope going to the input of that that diode, color changing diode. You see we got that ripple still, even though it's essentially not present at the output of our inductor. Well, I would suppose that LED, that ripple is going to have an effect on the lifespan of that LED. So I want to remove this ripple from here, but still keep my output very, very clean. Right now I've got that 100 microfarad and 22 microfarad capacitor right at the output. So what I'm going to do is I'm going to remove, and I know this is hard for you to see, I'll turn the light back on for a second. I'm going to remove this 100 microfarad capacitor from the output side, which is cleaning up our signal. I'm going to move it to the input side to clean up the signal through the entire circuit. So I'll turn the light back off, but I'm going to remove this, and hopefully you can see a slight change in our LED here. Okay, so light's going back off. All right. When I remove this 100 microfarad capacitor off of the back end, we get slightly more ripple back there. I'm going to move it over to the front end between the first leg of our resistor and ground. You see now we filter out there, and there was a slight, ever so slight reduction in the brightness of our LED, but we got rid of that ripple on the front end, and we kept the back end of our circuit very clean as well. So essentially, we've developed ourselves two circuits. Now that's going to fluctuate just ever so slightly because of that color changing LED. And the same thing at the output of our inductor. But at least we can save the life of this LED a bit because we've gotten rid of that ripple heading into it. Hold on a second, light's going back on. Okay. Now I'm going to swap out this LED, this light changing one, for a standard white LED with a 3 to 3.2 forward biasing voltage. Okay, and then again, this is without ripple on the front end and without ripple on our output. Now I'm going to remove that 100 microfarad cap at the beginning, and that LED got just ever so brighter. Did you see that? And our output got slightly dirtier. And I'll turn the light off for us so we can see it slightly better. All right, light off. No ripple on the front end. With ripple. Dirtier output. Unless if I put this 100 microfarad at our output, then we can clean it up. So, trying to short it out there. Yeah, cleaned it up slightly more. Now removed, less cleaned up. We'll put it back in towards the front. So there you go. And we can logically see a reason why we would want to, in this case, have that, watch your eyes, have our 100 microfarad capacitor at the front versus the back for cleaning out the output here. Now, let's say that you have an electronic device and this is your LED, which tells that the power supply is on. You would also want whatever this supply is feeding, saying if it was, rectified 2.2, 2.8 volts DC, you would want the output of here to be extremely, extremely clean. So we're basically taking a unregulated DC per se, and well, I can't really say that we've regulated it more, but I mean, we've at least filtered out the AC portion of it to give us a super clean signal here, as well as a super better clean signal here to save the life of our LED to let us know that our power supply is on. And then whatever device is powered by a 2.8 volt source, I can plug it right here at the end, and I'm assured that it's going to be a clean signal. So there goes our demonstration, and hopefully you've enjoyed it. I know I have. Yeah, I quite fancy myself a color changing LED. But anyways, I thoroughly have enjoyed doing this demonstration with you. When we come back to our DC components, I've essentially taught everything I would like to teach with DC. We'll actually build our first DC true DC circuit. We're going to build ourselves basically a flip-flop. So we're going to take DC, and through the components that we've learned about, we're going to build an AC circuit, which would be essentially our segue into AC theory and component theory concerning AC circuits. But anyways, probably rambling on for a bit. Thank you for watching. Take care and goodbye.
Mark?